Hi, my name is Mira Hahn, and I will be presenting our paper, No RL, No Simulation, Learning to Navigate Without Navigating. Imagine the scenario where you go to your friend's house for the first time and they ask you to go check on something on the stove. You don't know where the stove is, but looking at this house, we can imagine there are 3 possible paths to take to find the stove. Using the semantic priors we have from our previous experiences and observations in a variety of houses, we know the stove will be in the kitchen and we should take the path likely to get us to the kitchen, which in this scenario is path number 2. This task is fairly obvious and easy for humans, especially in structured indoor environments. Embodied agents have difficulty performing this same task. These semantic navigation tasks in novel environments are specifically hard for embodied agents because the goal location is unknown and the agent must make efficient and intelligent exploration decisions to find and reach the goal. To teach agents to succeed in semantic navigation tasks, they must learn the semantic priors of the environments as humans do. Learning these priors of the environments requires both large-scale datasets and diverse datasets. While reinforcement learning has worked for teaching embodied agents to navigate in tasks where a goal location is given, we find that teaching agents to perform semantic navigation in tasks using RL is unsuccessful. We attribute this to 2 main reasons. The first is that RL is not sample efficient. In semantic navigation tasks, which require the agent to explore, the number of steps required to learn to solve these tasks expands exponentially. The second reason is that there is a current lack of diversity in the existing simulator environments. RL agents trained in the simulators are limited to the number of simulator environments. Scaling up the dataset environments in terms of diversity and number is possible, but currently very costly. In order to overcome these limitations, we propose to learn a navigation method directly from passive data of trajectories of indoor environments. Our approach is called No RL, No Simulation, or NRNS, and we show that this approach can outperform reinforcement learning and imitation learning approaches on the task of image goal navigation. We find that RL and simulation is not needed to learn navigation. This is because navigation is a highly structured problem. Unlike RL, we do not need to do credit assignment. We can instead directly predict distance to goal for areas in the exploration frontier. Additionally, we do not need to learn a policy. We can instead use a greedy policy where the agent selects to go in the direction which minimizes its predicted distance to the goal location. Additionally, we do not need interaction data to learn to avoid collisions. We can simply use a depth-based policy to avoid local obstacles. Our approach, NRNS, can be described by the simple formulation. First, use depth to predict new explorable area without colliding into obstacles. Then predict distance to goal over the exploration frontier. Then greedily select to go to the area that lowers the total distance to the goal. We applied this proposed approach for the semantic navigation task of image goal navigation. The task setup for image goal navigation is an agent is placed in a novel environment with no map of the environment. The agent is given an image with a limited field of view taken at a goal location, but the agent is not given the coordinates of the goal location. The agent is tasked to navigating within 1 meter of the location where the goal image was taken and must do so within a set number of steps. Additionally, the agent has a limited field of view of 120 degrees. The agent receives RGBD observations and actuation post readings, and in our NRNS approach, the agent builds and maintains a topological map of the environment as it navigates in search of the goal location. The topological map that the agent maintains contains both explored and unexplored nodes, where the unexplored nodes represent the exploration frontier. The agent uses the topological graph to decide where to navigate to next in search of the goal image. The agent does this by using the greedy approach of navigating to the subgoal, which minimizes the agent's distance to the goal image. The agent learns a graph neural network over the topological map, which uses the visual features of the explored nodes to predict a distance to goal for each unexplored node. The agent then selects the unexplored node with the lowest distance predicted as the subgoal for the agent to navigate to next. After selecting the subgoal, the agent must make low-level navigational actions to reach the subgoal without collisions. Since subgoals are local to the agent's current location, the agent uses a non-learned depth-based policy to choose the low-level navigation actions to reach the subgoal. This is done via constructing a local obstacle metric map via depth observations. After reaching the subgoal, the agent expands the graph and then decides if it should stop exploring and do local navigation to what it predicts is the goal location. To expand the graph, the agent uses a non-learned depth-based approach. Using depth, the agent determines what are geometrically explorable areas on the exploration horizon, areas which will not lead to collisions, and adds these areas as unexplored nodes into the topological graph. After expanding the graph, the agent predicts if it should stop exploring. Additionally, it predicts the goal location coordinates. If the agent predicts to stop exploring, the agent uses the local navigation policy to navigate to the predicted goal coordinates. Predicting to stop exploring and predicting the goal location coordinates can be modeled with a CNN and MLP that takes as input the current image and the goal image. We have 4 functions now, and 2 of them, the distance prediction function and the target prediction function, are trained. The local navigation and graph expansion functions are depth-based. We now put them together to form our hierarchical approach to image goal navigation, and we show how this works for a given time step. First, given the current topological graph and the goal RGB image, the agent predicts the distance to goal for each unexplored node. It then selects the goal node with the lowest predicted distance to the goal as the subgoal. Then, using the depth-based local navigation policy, the agent takes navigation actions to reach the subgoal. Upon reaching the subgoal, the agent updates the graph with its new observations at the current location and then expands the graph with new unexplored nodes in the geometrically explorable areas. Before selecting a new subgoal, the agent also predicts if it should stop exploring and predicts the exact location of the goal. If the agent predicts to stop exploring, it uses the local navigation policy to reach the predicted target location. Here we can see an example of the NRNS agent using this hierarchical method to navigate a Matterport 3D house in search of the goal image. In order to train the distance prediction function and the target prediction function, we use passive RGBD video of indoor trajectories. We use the habitat simulator to generate random non-shortest path trajectories through training environments. We generate around 1K videos per training environment. In order to train the distance function and the target prediction function using these data, we need to transfer these videos into trajectory graphs. Using affinity clustering over the pose and visual features of stepwise trajectories, we can create graphs to train the distance prediction function and the target prediction functions. Note, we do not use the agent's actions along the trajectory. We add possible explorable area nodes to the trajectory graphs using the explorable area function. Now we can select the subgraphs of the trajectory graph as training data for the distance prediction function. Here we show the results of NRNS on the image goal navigation task on the Gibson dataset. We compare NRNS against popular distributed RL methods, which are directly trained in the habitat simulator for image goal navigation. Here we show the results for training RL methods with 5 to 10x more steps than NRNS and with 5x more episodes per environment. We show the results of a behavioral cloning baseline trained on the same passive video trajectories as NRNS, but with access to the actions taken. Using SPL, we show NRNS outperforms these baselines. However, in these results, NRNS is trained with random trajectory videos generated using the habitat simulator. We would like to remove any reliance on the simulator during the training stage and then test performance. To remove this reliance, we use the Real Estate 10K YouTube dataset of indoor real estate videos as a passive video training dataset for the NRNS method. We train NRNS using passive data from different sources, Matterport, Gibson, and Real Estate 10K, and report the results here when tested on Gibson data for the image goal navigation tasks. We see a small dip in performance between training on simulated data, Matterport 3D and Gibson, versus training on real-world data, Real Estate 10K. This is to be expected as we are still testing in simulation. We observe training on NRNS on Real Estate 10K still outperforms other passively trained baselines of behavioral cloning. In summary, we introduced the no RL, no simulation NRNS method, which is a hierarchical approach for navigation using topological maps, which only needs to be trained using passive videos of trajectories without actions. We demonstrate our method on the task of image goal navigation. On this task, we show NRNS can outperform well-known distributed RL methods that are directly trained in the simulator for millions of steps, as well as outperform behavioral cloning policies that have access to action sequences during training. To show our method does not need the simulator, even for creating passive videos, we show our method can be trained on in-the-wild videos from YouTube and still retain competitive performance on image goal navigation. Thank you for listening to our talk. To learn more, please check out our code and project webpage.